Alright, this is going to be our third and final video for the day. We actually have now wrapped up chapter 5, and we're going to start chapter 6. So, since we're starting a new chapter, in honor of starting a new chapter, I have some hiking pictures for you guys. New hike, and I think that I can confidently say this is my absolutely most favorite hiking trail in Arkansas. So there's some cool pictures here. This is a cave. They actually call it Arkansas Cave. I'll tell you the name of the hike in just a minute. I don't know if you can see. Does that kind of look like an inverted Arkansas? Anyways, they call it Arkansas Cave. And there's a waterfall coming out of it. You can't climb up in there or anything. Not that I would even want to. But that's a cool spot you get to towards the end of the hike. And then there's another cool waterfall. You can actually see both of these waterfalls at the same time. So you, like if you're looking at Arkansas Cave and then you turn to your right, you will see this other waterfall, and I made my husband stand by it so you could get a visual how big it is. Not too terribly big, but pretty cool. And then that's not even the coolest part of this hike. These are just a few cool elements. The coolest part, I guess I should tell you the name of it. It's called Indian Creek, or the nickname of this trail is Eye of the Needle. All right, so if you can imagine a needle and then the eye of the needle where you thread the needle, put the thread through, that's what it's like named after. And that's because at the very end of this hike, the grand finale, is you get to this huge rock structure that kind of looks like the eye of a needle. And so it's kind of a thin area between this massive, massive rock. And this is kind of like a down and back type of hike. You hike all the way to this point, and then you hike back out the same way you came in. And so we actually ate lunch here to show you kind of scale-wise how big this structure is. Next picture down is just you can't even see the top of the eye of the needle. Here I am down here. I didn't get very far, but trying to climb up. And so, anyways, it's really grand, and it's just really awesome because of that. So, there it is, Indian Creek, Eye of the Needle. If you start at Kyle's Landing, okay, so this is a campground in the Buffalo National, or the Buffalo River area, Ponca area, if you ever go canoeing. Kyle's Landing is a campground around that area, and it's a very popular spot to put in or get out of the river. And the trailhead is at Kyle's Landing. Can't spell. Anyways, so if you're going to go hike this, I would plan all day. Like, it's going to take you a couple hours to get there. It'll take you several hours to hike down and back, and then you'd have to drive back. I don't advise taking, if you had like a pet, I wouldn't advise taking a dog on this trail, because there was a part we kind of had to climb, and I just don't think a dog could do it. So anyways, really fantastic trail. It's my favorite one for sure. I need to go do it again. It's been a while since I've done it, but happy to share that one with you guys. So let's get into chapter 6. We're going to talk about moles and mass relationships, and I don't mean like a mole on your skin. Or if you've never heard of the word mole before, it's a term that stands for a value, a quantity. And we're going to understand how that relates to mass. And kind of to segue into this topic, I want to look at this picture here, which has some recommended daily intakes. So we know, I don't know how many of this particular class are nutrition or future dietetic students, future dietitians, but we have some recommended daily intakes for different vitamins and elements that our body needs every day. So for the first one, iodine here is important for our thyroid. Almonds, raw almonds are good. I love almonds. My favorite kind of almonds are dark chocolate covered almonds. That literally might be my most favorite snack ever. But men and women both need about 150 micrograms a day. So not a ton, but we need it. We don't want to deprive our body of it. We know we need a lot of vitamin C. right? Vitamin C is like a pretty essential nutrient. You can get it in other things besides orange juice, though. I used to just be like, if I need vitamin C, I'll drink a glass of orange juice. You can get it in broccoli, all sorts of vegetables. Men need about 90 milligrams a day. Women, 75 milligrams a day. And then iron, red meats are a good source of iron. And men need 17 milligrams a day. Women, 13 per day. And so, obviously, this is not a comprehensive list. But I wanted to bring this up because, vitamin C is a molecule, okay? And, well, it's actually a package of molecules. Vitamins are huge. Anyways, iodine is an element, and it's a diatomic element. Iron is an element, and our body needs a certain amount of these, and we communicate these amounts in mass, right? And my question is right down here. How do we know how much of each nutrient our bodies need each day? And these can be pretty important, too, especially if you have any sort of autoimmune diseases or specific diets you have to follow. It might be tricky to get some of these, not these three in particular, but it might be tricky to get your nutrients if you are like gluten-free. You might have to think about some things, or if you're, nut-free or whatever. And so how do we know how much of each nutrient our bodies need every day? I'm really not even going to answer that. Obviously, we have people who study this and come up with these recommendations. But what is tied to this question, and what I want to point out, is that our bodies see and process molecules. And so I guess what I'm asking is, how do we go from molecules, because we don't really think about the number of molecules we're eating, right? But how do we go from molecules to things like this, the mass, 17 milligrams? How do we go from molecules to mass? How do we make that transition? And it's also the way we buy and sell and cook and work. We work with units of mass, not with units of molecules. But our bodies work in units of molecules, right? For example, you go to the store, you buy a bag of sugar. You buy a 10-pound bag of sugar. You don't buy a bag of sugar that says it's got 60 billion molecules of sugar in it, right? This is a topical anesthetic. So if you got a cut, and my sports medicine people, pre-PT, you might spray this anesthetic to kind of locally numb your skin or injury. And this is a terrible view, but it says it's got 3.5 fluid ounces in it. Not, 60 billion molecules. We don't buy in terms of molecules. We buy in terms of mass, in terms of weight. So, to go back up here and think about this, this is where the mole comes in, okay? To relate between mass, units of mass, and then number of molecules, the mole was developed, all right? So, if we're going to use the mole, we need to know how much molecules weigh, all right? I'm going to say that again. If we're going to use this term for its intended effective purpose, we need to know how much a molecule weighs, all right? So that's this idea right here, molecular weight. We need to know the molecular weight of any molecule we're going to deal with in any reaction or any drug we might come across if we're in a health science setting. We might need to calculate its molecular weight. And to do that, how do we do that? To do that, we need to know a molecule's, I think that actually is these first two blanks, molecular weight. Meaning how much one molecule weighs. And we need to know how many molecules of a given substance are in a certain mass. How many molecules of a given substance are, if I said I had 10 grams of hydrochloric acid, we would need to be able to calculate how many molecules of hydrochloric acid that is, okay? And we will get to those things. So to calculate a molecular weight, the way you do it, it's the sum of the atomic mass for every atom in the molecule, right? And if you're dealing with an ionic compound, we call it a formula weight. So let's look at some example molecules. Let's go back to this topical anesthetic spray for just a minute. The way they make this anesthetic spray is you take ethane here, C2H4, well, ethylene actually, ethylene, and hydrochloric acid, or hydrogen hydrochloride. And those can be combined to give you ethyl chloride is the name of this molecule right here. You don't have to memorize these names, but that is the active ingredient in the anesthetic spray. So let's calculate the molecular weight for each of these molecules, which is what I'm going to do down below. And this is going to be the last slide for this video, and we'll be done for today. So here's our reaction. Let's calculate the molecular weight of C2H4. And remember, we just need the atomic mass, and we need to know how many of each atom we have in our molecule. So I see that we have carbon and we have hydrogen. You will want a periodic table handy. I obviously don't have one on this slide, and I don't have one above or below. So you might want to pause this video if you need to. Go snag a periodic table or pull one up on your computer or on your phone. We need to know the atomic mass of carbon. All right. I'm going to write down that I have 2 carbons, and I'm going to say 2 times what is the atomic mass of carbon. All you're going to do is look at a periodic table, and you're going to get the mass of carbon off the periodic table. And if you're looking at the right square, you should see that it's 12.011. All right. Now, the units here are actually atomic mass units, AMUs. Right? When we do this math, we get 24.022. So that's the total mass of this molecule just contributed from the carbons is calculated there. But we also have 4 hydrogens, so we'll say 4 times. Again, look at the periodic table. 1 point. You'll have to round. I usually do like 3 decimal places. I think it's 008. And so then the AMUs. So you want to do 4 times 1.008. 4.032. Is that right? Hope it's right. And then we would add these up together. So okay, so this is how much a molecule of C2H4 weighs in atomic mass units. Okay, let's do HCl. Hydrogen, chloride, we just have 1 each. So we just say 1 times 1.008. And then chlorine, 1 times, if I'm looking at the right square, it's 35.456, I think. And so obviously that's just the same. AMUs here. And then we want to add this up. So that would be 30. We'll do math the old school way. I didn't line it up properly though, right? There we go. I think that should be right. All right, and then you could calculate the mass of this last one. I'm going to point something out. This is a combination reaction, so the mass of this plus the mass of this is going to be the mass of that, our product here, ethylene chloride. So all we're going to do is, it won't always be this way. If it is a combination reaction, it will be. But you could write out the carbons, hydrogens, and chlorines like I did on the 2 previous. But to save time, I'm just going to say, all right, 58.54 plus 36.464. Does anybody remember how to do math this way? Is this how y'all still do math? Y'all just probably punch in a calculator. Okay. That's what I got. If I'm wrong, I'm sorry. I'm not checking on a calculator, but I hope that's right. So anyways, this is how you would calculate the molecular weight. That's what MW stands for here. The molecular weight for each of these molecules. And I'm going to pause this video here. We're going to pick up with this next week, and you will need to know how to do this for the exam. So please reach out to me with any questions you have or had if something did not quite make sense in these first few slides of Chapter 6.